Hello viewers, you're welcome to this tutorial. Today we'll be looking at complex numbers. So we'll say complex number. It's not complex. So let's start. We start by knowing the representation. We have the conjugate of a complex number. Modulus, polar form of the complex number. De Moivre's law or theorem. Euler's formula. Nth root of a complex number. And finally, solve real exam questions. So let's get started. So representation. A complex number is written as anything of this form. C equals a plus ib, where a is the real part and b is the one that has I is the imaginary part. So whenever a number is splitted this way, know that it's a complex number. So example, if you have 5 plus I6. So our real part is what? 5. While our imaginary part is 6. So again, though you can write our real numbers are also complex numbers, because 5 could be written as 5 plus I0. So a real number is a number that the imaginary part is 0. Do you get? As you can see, 5 is a real number, and 5 could be written as 5 plus I0. So it's also a complex number. Okay. So the next thing is the conjugate. Conjugate of a complex number is just what the conjugate is another complex number that converts it to pure real number. So I'm saying that if anything that you multiply, the complex number that you multiply with the complex number to remove the I part of that complex number, that's to convert it to pure real number, it's called the conjugate. We normally denote it as Z. So I'm saying that if Z is A plus IB, so Z bar, the one that has bar on top, is now the conjugate, and is always the opposite. That's the opposite of the imaginary part, minus. So this is the conjugate. So because if you multiply A plus IB times A minus IB, okay, let's multiply this. A squared, this difference of 2 squared minus IB squared, this A squared, I squared, B squared. Okay, I didn't say something about this I. I is the square root of -1. That's the main thing they introduced complex number, because most times after solving, to find the nth root of negative number becomes a problem. So that's why they now introduce this I as square root of -1. So from this you see I squared, A squared minus I squared, okay, which implies squaring both sides here. We have -1, so I squared is -1. So we now have minus, so we have plus B squared. So what do you notice? We don't have any imaginary part again. So anything that removes the imaginary part is called the conjugate. So we denote it by putting a bar on top of the Z. So that's the conjugate. So example, if someone asks you find the conjugate of 3 minus I 2/5. The conjugate is conjugate is 3 plus I2 over 5. Just change the sign of the imaginary part. That's the conjugate. So the next one, the modulus of a complex number. The modulus of a complex number is written as absolute value of z, and is always the distance from the origin. Okay, I will use an Agard plane to. I'm saying that let me draw an Agard diagram. So this is the real part. We don't normally call it. We call it Agard diagram. Or Agard plane. So why this is the imaginary? So assuming this is a complex number, this is our A, our real part, and this is our B. So the distance from the origin is the modulus. We denote it by putting absolute value bar here. And if you check using our Pythagorean theorem, from Pythagorean theorem, you see that z is z squared equals a squared plus b squared, which implies that z itself, absolute z, is now that. So meaning the sum of the square root of the sum of the squares of the real and imaginary part is the absolute, the modulus or magnitude of a complex number. So example, someone asks you find the modulus of 2 minus 3i or i3. So the answer is just 2 squared plus 3 squared in square root, which is 4 plus 9, 13. So that's our modulus. Okay, let's proceed. Polar form. Okay. Polar form is just the trig aspect of complex number. What we've been representing since is the rectangular Cartesian form. So the A plus IB is the Cartesian form. So I'm saying that this is our Cartesian. Okay. The formal representation we use is the Cartesian. So if you see a complex number of this form, A plus IB, this is our rectangular form, or I call it Cartesian form. So that's it. So let's now convert it to trig, which is polar form. So let's use our Agard diagram to do that. So if you have, this is our real part and this is our imaginary part. So assuming this is the complex number z equals a plus I b. You know, this is our A and this is our B. So from trigonometry, you know, from here to here is B, and this is A. From here to here is A. So from trig, let's bring in an angle, theta. This theta is called an argument. So theta is the argument. Call it the argument of the complex number. Though a complex number has many arguments, because you can still read this from this side as moving clockwise direction. That's also argument. Beta is also an argument. They are all argument. So let's continue with what we have. We are using theta. So from here, you notice that A, using our, okay, A now. So from sine theta, there are three sine thetas. Sine theta is opposite over hypotenuse. So again, remember our hypotenuse is, let's use z bar, our modulus, to represent the hypotenuse. Is opposite, which is b over z bar. Again, our cos theta is what? Adjacent. So a over z bar. So making b the subject of formula here, b is now z bar sine theta, while a is what? Z bar cos theta. So let's now go over to our Cartesian representation and substitute this. Therefore, z is now a plus ib, which is, what is a? Z cos theta plus ib is what? Z sine theta. And what do you notice? They have z bar in common. So bringing it out, we have cos theta plus I sine theta. So this is now our polar form. We'll be using it a lot here. So this is the polar form of a complex number, where theta is called the argument. Again, you can see that theta, from that same diagram, theta is tan inverse, that's tan theta is opposite over what? Adjacent, which is now tan inverse of the imaginary part, which is b over a. So the argument of any complex number is arctan of imaginary part over the real part. So that's in case if you ask to find the argument. But there's what you call principal argument. Any argument that falls between such that minus pi is less than that and is less than or equal to pi, this theta is called the principal, call it principal argument. We normally use capital letter for that argument. So once you see a capital letter, it means that it's the principal argument. Because I told you a complex number has a lot of argument, because this is trigonometry, we move in a circle. So I'm saying that normal argument is always the principal argument plus 2 pi k, where k is from 0, 1. Do you get the rotation? So that's it. So any argument that satisfies this is down the principal. Because, okay, example, if you ask to now convert a 2 plus I2 b, okay, 2 1 minus I to polar form. So the answer is very, very simple. Using our formula, we can do that. But I always advise students to draw the agar diagram, especially when we have negative, because it will fall either in second, third, or fourth quadrant. So always use it to make our equation, to make our solution correct. So from here, it's very simple. So drawing an agar diagram for this. So this is our real part, this is our imaginary part. So 2, 2, so 2, 2. So from here is our theta. Yes. So this is our complex number, z equal 2 plus I2. So you don't need to waste time. Our theta is tan inverse, that's our argument, tan inverse of 2 over 2. Which is tan inverse of what? 45, 1, which is 45 degrees, or pi over 4. So if you don't use, we normally use radian measure here. This is pi over 4. So why our modulus is 2 squared plus 2 squared in square roots. So 4 plus 4, 8, so square root of 8. Or maybe you can write it as 2 root 2. So anyone. So therefore, this is now our complex number in terms of polar form is now root 8 cos, what is our pi? Our theta, pi over 4 plus I sine what? Pi over 4. Again, the answer could be, I told you the argument could move. Remember, we moved counterclockwise. We can move clockwise. This is also the argument direction. But we normally take this as positive. The actual direction, which is the counterclockwise, while the clockwise is negative. Yes, I'm saying that if this is it, you know, the remaining angle is now 2 pi. Whatever that is here is 2 pi minus pi over 4, which is 7 pi over 4. So I'm saying that if we don't write it this way, it's now root 8 cos minus 7 pi over 4 plus I sine what? Minus 7 pi over 4. So if you don't write it this way, you write it that way. Okay, this is root 8. Remember, cosine is an even function, so we don't need the negative sign, so which is 7 pi over 4. Y sine is an odd function. Sign of negative is that. So the answer could be this. Could be this or this. So please don't make a mistake. You might see this one in the option. So whenever you move clockwise, negative, the argument is negative. Why the angle now is now 2 pi minus the argument, the former argument. So the other question, if you are given, they say I minus 1 minus I. Okay. We'll draw an agar diagram for that. So minus I minus. So our meaning here, this is 1 and this is also 1, negative. So this is our complex number, 1 minus I. So our argument here is either this way, we'll move clockwise, we'll move anti-clockwise, or we'll move clockwise. So let's remember, this is our positive sense. Why this is our negative sense? This is our negative sense. So we are looking, let's call this our beta now. That's beta. So notice that beta is now tan inverse of 1 over 1, which is pi over 4. But remember, in the negative sense, therefore, our modulus is 1 squared plus 1 squared, or in square root, which is root 2. Therefore, our complex number is now root 2 cos. Remember, this is the negative. The actual argument is this, the positive. Why this is the negative? So if you use the negative sense, this is minus pi over 4 plus I sine minus pi over 4, which is root 2 cos. Told you this is always positive, minus I sine pi over 4. So that's the answer. Or you use the positive sense, which is now 2 pi minus that. Or root 2 pi minus that is 7 pi over 4 plus I sine 7 pi over 4. So anyone is the correct answer, either this or this.